Our three versions of the confidence interval formula are up here. The first two are for a mean. I want to be confident that the population mean mu is within the interval given based on my estimator x bar, but that depends on whether I know the population standard deviation somehow, or I'm estimating it from the sample standard deviation. And that's why we use sigma versus S, but that's also why we use T instead of Z. My T distribution accounts for widening, putting a little more emphasis out in the tails on the outside edges because I have an unknown population standard deviation. For a proportion, pi, we're using our estimator P, the sample proportion, and we're assuming we have a large enough group where we've had at least 10 successes and at least 10 failures. And that allows me to use the normal distribution again, or at least to assume it. And I use Z one more time. All of these assume I have an effectively infinite population. I've heard that phrase before. It's been quite some time since I heard that phrase. Back in chapter 2, what does it mean for population to be considered effectively infinite? Felix?
Smaller than 5%. Look at like sample of 14 out of like 500 or whatever. Smaller than 5%.
Wonderful. My population is effectively infinite if my sample is less than 5% of the population. When it isn't, then I sample a larger percentage of the population. Sampling without repetition, without replacement, becomes hard. This might be the wrong word here. In statistical terms, when we talk about controlling for something, we talk about making a correction to adjust for bias inherent in the action we are doing. For example, surveys of use of illegal drugs tend to have wildly underreported numbers. Anybody want to guess why?
People don't want to get in trouble for using illicit drugs.
It's kind of hard for me to ask people, hey, are you an underage drinker? When knowing that if you are, you'll get arrested. It's a bad thing, right? You're going to have dramatic underrepresentation. So the assumption is for every person who admits there's at least two more that didn't. And so what do? In sampling, the assumption is you're going to triple the numbers. That's controlling for a bias that's inherent. I like the word correct a little bit better. Textbook flips back and forth between using this, and the language of statistics does talk about controls more often. If I'm sampling out of a larger fraction of the population, if I sample without replacement, I'm going to get more variation. And that means my margin of error will be bigger than it should be. So up here in our actual formulas, I'm taking my estimator and I'm taking give or take a bit. There's my margin of error. I want to adjust that and narrow it with a correction for a finite population. It's even called a finite population correction factor. And it's given by this formula. I take my population size, subtract the number of people in my sample, divide by population size minus 1. What can you guarantee me about this factor? Just as a number. Do I know anything about this number? Well, that would be this number up here. Little n over capital N would be greater than 5%, right? But this number down here is going to be different. Felix? It can never be bigger than 1, right? Because if you're sampling a finite number of people from another, little n's got to be bigger than 1 person. Otherwise, you're not taking sampling, you're taking 1 data point. That's not a sample, that's a wild ass guess. So the biggest this number could ever be is 1. And that's what I'm going to say, oh, that's my way of shrinking the margin of error. I'm going to multiply my margin of error by this number. And that changes all 3 of these formulas by adding, well, multiplying in, the finite population control factor here. So I now get my average with known standard deviation formula. It turns into this. I just multiplied that on the end. Same thing with the unknown standard deviation. And the same thing for the proportion. All 3 of these formulas appear on page 299 in a box labeled formula 8, 13, 14, and 15. But we should only use these formulas in the cases where we figured out, exactly as Jason said, hey, this population isn't infinite, it's a finite population. my percentage of observed people is more than 5% of the population. Here we go. A random survey of 500 students was conducted from a population of 2,300 students to estimate the proportion that had part-time jobs. The sample showed 245 had part-time jobs. Well, 245 out of 500 is what percent? $245 out of 500? Almost a half, 49%. So I want a 90% confidence interval for that proportion. I think if I looked at all of them, it'd be around 49%. What's my range? First question. Which formula should I be using? Because I'm looking for a proportion. That's the third formula we were looking at. Second question. Infinite population or finite population? I need a percentage. How big is my sample as opposed to my population? I'm pretty sure it's not half. You're talking about the number of people that responded with the job against the number of people in the sample. Because the population of students is only 2,300. But 500 out of 2,300 is bigger than 0.05, right? This is a finite population, which means I shouldn't just be using the proportion formula. I should be using this version of the proportion formula. So I can now go through and perform this actual calculation for problem number 41. Little n was 500, capital N was 2,300, X, the number of people who gave me a positive response, was 245. And that means that my proportion, 245 out of 500, was 0.49. We were asked for a 90% confidence interval. This proportion formula uses Z. Felix?
Wasn't that 1.6?
How do we find out?
Yeah.
Yes, I need to go to the appendix tables. If I'm doing a 90% confidence interval, that means 10% is on the outside. Half of it low, half of it high. I need alpha is 0.10. So I'm looking for Z alpha over 2 or Z 0.05, which is wonderful. Why are you giving me a headache, pen? Now, I can look that up in two different ways. In table C2, I can go to finding the number that is closest to 0.05, but if I look in my table, I'll see 0.495 and 0.505 for 164 and 165 respectively, and that's why I split the difference. There was also a table earlier in this section that listed all of the critical numbers we end up using most often for these confidence levels. I wrote it down. Here we go, bottom of page 279, 1.645 for 90%, 1.96 for 95%, 2.576 for 99%. And since those are the most commonly used, I'm going to hang on to those numbers. but we had a T table, didn't we? In Appendix D. There was a whole nother list of numbers in the T table. So pull up Appendix D for a second. I want to show you something neat in that appendix. Appendix D, we have confidence levels listed at the top, right? And the degrees of freedom are the first column here. And as the degrees of freedom get bigger, we get closer and closer to a normal distribution, right? All the way at the bottom of the right column, 90% confident, 95, 98, 99, 80. What's that symbol right there? Say it louder, Haley. Which means these are the numbers for the Z table. I don't have to look them up in Appendix C. I can look them up here. These are the Z numbers. 90% confidence, 1645. 95% confidence, 196, and so on. So I can get them in several different places. I could also use my technology to do the inverse normal. But now we have this number. Great. Let's compute. I'm going to use this formula right here. My confidence interval will be P plus or minus. P is 0.49. Minus the first time. Z alpha over 2 is 1.645 times P times 1 minus P. P is 0.49. What's 1 minus P? Twitch. Try again. 0.51. And then that's divided by little n, 500, all under the square root. And then my other square root is the finite population factor. So that's 2300 minus 500 over 2300 minus 1. That's the low end. The high end simply replaces the minus sign with a plus sign. The calculation is a little uglier because of the finite population control factor. But everything else mirrors exactly what we did last week. 0.49 minus 0.49 times 0.51 divided by 500, close that square root, times make a new square root. 2300 minus 500 is 1800, divided by 2299. There's my low end. We get a really small decimal here, right? That makes sense. We're talking about a proportion. We're saying now 45.75%. However many decimal places is appropriate. It's going to depend on the problem. I started with nothing here being larger than two significant digits, but I'm looking at 2 decimal places here, 3 decimal places here. I don't really want to go out much past 4. So I'm going to go ahead and call this 4575. And then I'll replace this minus sign right here with a plus sign. Matter of fact, I'll just hit enter and back up until I can get to that plus sign. 5225. My sample said that less than half. Up, 1 minus p. Oh, yeah, I absolutely want p and 1 minus p because you're right. If I had a negative under that square root, it'd blow up my calculator. No negatives under my square roots. We save that for the complex variables class. That's fun stuff, but it's not this stuff. My sample told me that just under half of the people at this school who are full-time students have a part-time job. But for me to be 90% confident in my answer, it could be anywhere between 45.7475% and 52.25%. It's a range, right? I'm 90% the actual, if I surveyed all 2,300 people, the actual number's in there. 90% certain. It could be wrong. I could have gotten a really whacked out sample, and maybe the correct answer is 60%. I don't know. I'm only 90% confident of this. But you see how the correction factor narrows that? If we'd assumed this was an infinite population, if I delete this part, I get a bigger answer here, right? If I use the -1, I get a smaller answer here. It's not a huge difference, but it is a wider interval when we assume that the population is effectively infinite, because it is less likely for us to get a really whacked out sample. Questions? How'd they pick 500 people? How'd they decide that was who they were going, how many they were going to sample? Sometimes we work backwards. We say, I want a particular margin of error. If I'm doing a proportion, maybe I say to myself, I want a 2%, 0.02 margin of error. Maybe for a mean number of hours studied by a student at Seton Hill, hoping that's a nice big number. But I wanted to say, all right, I want a margin of error that's no more than an hour and a half on each side. How do I figure out how many people to ask? Okay, hang on a second. Our formula is for a mean. If I assume we have an infinite population, I do this. Well, then this piece right here, that's really what my margin of error is. I want you to rearrange that. Solve for n. Let's get n all alone in that formula. A little bit of rearranging. If I multiply the square root of n over, I can then divide by e. And then I can get rid of the square root by squaring everything. Since this is a number of people or items or whatever that I'm sampling, I want to round up. There are some interesting things that now show up in this formula that kind of inform me about the way I should think of my sampling. I want to ask enough people based on how confident I want to be. That's why I need the alpha level in there. And what my expected error is. The units for E need to match the units for X and sigma so that these will have the same unit and thus cancel out because Z has no units at all. So if I'm talking about hours of studying, I want to measure my error in hours, my margin of error. If I'm talking about percentages, I want to give an error in percentage points. If I'm talking about salary in dollars, I want to give an error in dollars. The average salary of a Seton Hill faculty member is with a margin of error of how many dollars? I have a problem with this one. Sigma. What's sigma again? Oh, crap. I have to know something about the whole population, and I'm not even doing the survey yet, right? I'm trying to figure out how many people I should ask. How the hell do I get sigma? I could use S, right? Instead of sigma. I could do a sample and get the population instead of the population, get the sample stand. I got to do a sample before I can figure out how many people to sample. That seems cracked in the head. I can go back to past data. If I've done similar samples before, I could use the standard deviations from those. I could average the standard deviations from those. I could kind of play some guesswork here.
Say that you're doing the sample of the entire population.
At which point I'm not sampling, I'm censusing, right? And that's if I've got a huge number of people, are you willing to really do them all? We're going to ask every single person on campus how much they study. I'm going to get a lot of no responses, right? Click. But I could make some other assumptions. If I was actually willing to ask everybody, then I really wouldn't be doing any sampling at all. I'd just ask everybody and get an exact number. I'd get the population. I wouldn't have to worry about a margin of error. But I could say, well, let's make an assumption about the population. Let's assume that it's uniform. Wait a minute. All right, wait a second. If I'm assuming a uniform population, now I can go back to my uniform distribution. Let's go to the continuous one. You have a formula for the standard deviation of a continuous uniform distribution. For most of you, it was on the formula sheet you used on the exam. For those of you that didn't put it there, it's in chapter 7. Go look it up. The very end of chapter 7, where the questions were, there are all the formulas we used in chapter 7. You'll find it in that. Felix?
That square root, then b minus a plus 1, then squared plus minus 1 divided by 4.
That's the discrete version, not the continuous version. The only difference is that minus 1. So here, I get this. Now, this means I need to know what the low is and what the high is. Well, if I'm talking about study hours for Seton Hill students, I know what the lowest possible number of study hours is. What's the lowest possible number of study hours? What's the highest number of study hours? We were talking about per week. What's the highest number of study hours you could have per week? Conservative assumption. There are only 168 hours in a week. You're going to spend at least some of that in bed and some of that in class. I know no one on campus gets 8 hours of sleep a night. But let's rough it and say people get at least 6 hours of sleep a night. That's 42 hours. Take that away. People spend the time in class. Based on your number of credits, you should be spending roughly an hour in class for every hour of credit you've got. Most people have between 12 and 18. We'll go with 15 credits. So that's another 15 hours I can take off. Y'all eat and sleep. You eat and use the facilities and socialize. I don't know, another 20, 30 hours. What are we down? Let's say we're 30. What are we down to?
81.
Okay. It is potentially possible that you could be studying 80 hours a week. Right. That's not even close to reasonable, is it?
Are you also taking account for homework hours?
I didn't take any of that into account, right? So we got to take more off. Let's go down to 60 hours. Homework is always more than classwork. But now I've got an estimate for the high and the low, and those are A and B. That's what these numbers are here. A and B are the low and the high. So if I can figure out an estimate for the low and the high, then I can use this number. So if I come up with 60 as a maximum number of hours somebody could study, I could go 60 squared over 12, take the square root. I've got a number. Square root of 300 is 17-ish, I think. But this is a really big estimate for the standard deviation. Why is this a big estimate for the standard deviation? This has nothing to do with study hours or my ability to predict what students are doing. This simply has to do with the fact that I made the assumption of a uniform distribution. What's a uniform distribution look like? Which means there's no central tendency, right? Everything's the same height, no matter how far to the left or how far to the right you go. If there's no central tendency, then everything is spread out equally. That's going to push the standard deviation out a ways, isn't it? That's why this overestimates the standard deviation, because it assumes there's no center at all. Which makes this a conservative estimate. It gives you a really wide confidence interval and means you should sample a lot of people to make sure you get people all the way across the spectrum. But that's assuming a uniform distribution. I could assume that there's a normal distribution. But normal distributions start with needing to know sigma to know what which normal distribution I'm on, right? That was how we figured out what our normal distribution looked like, was to know the sigma. But we had another way of kind of guessing what sigma was. Again, based on the high and the low. 3 standard deviations on either side. What's our area? Plus or minus 3 standard deviations. It's actually higher than that, right? It's 99.7%. It's really almost. So if I know that there's 3 on each side, I could take that high versus low, divide it into 6 pieces. And that would be an approximation. But again, this is an assumption that my population is normal. And this may actually not be conservative enough. This may be too small and be an underestimate for sigma, because as I just said, that gives me 99.7, not 100%. So I might actually need a little bit more. You could do all of these and then kind of see what difference it makes. I could take the average out of all three of them, right? Historical data and normal and uniform, and I could try and average those. But then I'd be like, well, do I have a lot of historical data or just a little historical data? How should I weight those? We could do a weighted average, right? I have also, this is where statisticians end up making their money. Because they start saying, how do you assign the weight? How much credibility do you give each of these options? And that's really, most of the time, a very subjective piece of behavior. So here in problem number 49, the combined city highway fuel economy for a 2016 Toyota 4Runner 6-cylinder 4-liter automatic 5-speed is normally distributed with range 17 to 22. If I assume that's a normal distribution, I can estimate the standard deviation. 22 minus 17 is divided by 6 is 0.83. There we go. Now, with that in mind, I could say, how many people do I need to survey? How many cars do I need to look at to have a margin of error of 1/2 of a mile per gallon? There we go. And that, you'll notice, doesn't actually care what the mean is. If I just want to figure out how many people, 90% confidence interval. What's my number for 90%? The same number we used up here. Great. My standard deviation you just gave me is 0.83, and my margin of error was 1/2 a mile per gallon. Standard deviations in miles per gallon, errors in miles per gallon. I can now work this out. That was problem number 49. Sigma was 0.83 over 0.5. I take that whole thing and I square it. What number do you get?
We have 0.5 again. Get that.
That was the margin of error requested in the problem.
Wow.
Hang on a second. Oh, I misread it. Stop. It's not 0.5, it's 0.25. Got to write down the right number. It helps if I copy the book problem out of the book properly.
Big piece that's for marginal error.
Yes. And it has to be given in the same units as our standard deviation. So I take that number and I square it. And then I round up. So I should be doing 30 people. By the way, if you were to, instead of using 0.83, use 0.833333, more threes, then this number would be 30.01. And you round up to 31. So if I want to get an accurate idea of what the average miles per gallon on a Toyota 4Runner with that particular engine and regular gas and all that fun restrictions, I need to survey 30 vehicles. Questions? The same idea works for a proportion. But my margin of error came from a different thing in a proportion. Same thing, this is E, my margin of error. So if I solve I'm going to get rid of that square root. E equals Z alpha over 2 pi 1 minus pi over n. I'm going to square first this time to get rid of the square root because it's only on part of the thing as opposed to just being on the n. So I have E squared equals Z squared pi 1 minus pi over n. Oh, I'll multiply the n from the right to the left and I'll divide the E squared. Notice that in our previous example, everything was squared, right? I took the whole thing and then I squared it. In this case, the proportion that we got isn't squared. It's multiplied by 1 minus. So it's the chance of success and the chance of failure put together like our binomial behavior. Again, how do I find pi? I can use historical data. I can take a preliminary sample. I can make the assumption of the most conservative possible option. The most conservative possible option here is to assume that that is 50%. If this is 0.5, so is this. And that's the biggest that value is going to get. So again, the question becomes, do I have past data? Should I give it any weight? Should I just make the assumption, well, assume it's 50%, we'll go from there. And then I'll figure out how many people to ask or how many pieces of information I want. And if I change my confidence level, I can change this Z value, right? If I was 90% confident, that's a lower Z than if I'm 95% confident. That's a lower Z than if I'm 99% confident. So if you start by saying, I want to be 99% confident, then you realize you're going to have to do 1,000 surveys. You go, all right, I'll settle for 95% and make the number smaller. Now, in this case, these numbers are proportions, so they're decimals, which means you can give E as a percentage. Oh, I want to be 3% on either side of the right answer, or 5% on either side of the right answer, or 1%. Well, just turn it into a decimal and then we're all in the same units all the way through. When I'm in my confidence interval, I'm pretty sure I know what's going on. When I'm out of my confidence interval, what does that mean? That's what we'll pick up on Wednesday. That means that we have just reached the end of chapter 8. That means homework on Friday. I will see you all on Wednesday. Have a wonderful rest of your day.